let's have a look at this thing called integrations, the inverse operation to differentiation, because like everything in maths has an inverse. Integration is the inverse of differentiation. We're going to start off by trying to solve a problem, and that problem is, how do we find the area under a curve? Now, we got lots of formulas for areas. We can find areas of rectangles, trapeziums, triangles, rhombus, all sorts of shapes we've got formulas for. But there's a lot more shapes that we don't have formulas for. But we'd still like to know the area. How do we do it? We'll do it via this example here with our cubic. Say we had to find the area between the x-axis and our cubic. Now, I could estimate it. Estimate it with shapes that I do know how to find the area of, and probably the first thing you ever found the area of would have been a rectangle. So we'll estimate it with rectangles. So I've just broken it up into two rectangles there. Now clearly that area is not going to be correct. It's going to be too much. But at least I'll know that the area under that curve has to be less than the amount of these two rectangles. So I could work that out. I've made the width of each of these rectangles just 1 unit, and the height would be whatever we get when we substitute those x values in. So for the first one we'll get 1 cubed, for the second one we'll get 2 cubed, which becomes 9. So I know the area is going to be less than 9. But that's an overestimate. But I could also create an underestimate by drawing two different rectangles. And in fact, the first rectangle is just a horizontal line. It has no height at all. But the area of those blue rectangles would be less than the area under the curve. So I'll work those ones out. Again, the width will be 1, and the first one has a height of 0, and the second one has a height of 1 cubed, which is 1. So I do know that that area is somewhere in between 1 and 9. If I had to do an estimate, I guess the logical thing to do would be to average those. So I'll estimate it at 5. That would be the average of 1 and 9. Now it turns out the exact area is actually 4. Not a great estimate. But we could do it again, but instead of having a width of the rectangle being 1, let's make the width of the rectangle 0.4. So in other words, I've created 5 rectangles. By doing that, my overestimate, you would see, is less than what it was before. So the width of each one of those is 0.4. The height of the first rectangle would be 0.4 cubed, and the next one 0.8 cubed, and so on. I now know that the area under the curve is less than 5.76. I mean, I put equals there as well, because theoretically I suppose it could be, but we know it's not, but theoretically it could be. If we do our underestimate, so let's draw 5 rectangles in there, and that would give me a value of 2.56. So I now know the area is somewhere in between 2.56 and 5.76, and if I was to average those, I'd get 4.16. Remember, the exact amount was 4. So we've got a lot closer straight away. All right, well, let's make it 10 rectangles. Let's draw all those 10 rectangles in, a lot thinner. The overestimate now is a lot smaller. The width of each of my rectangles is now 0.2, and the heights would go 0.2 cubed and 0.4 cubed and so on. That's 4.84. If I do the underestimates, and by the way, I'm using the word overestimate and underestimate here. Often you hear the term outer rectangles for the overestimate, because they're the ones that go on the outside of the shape, and inner rectangles for the underestimate, because it's the one that goes inside the shape. And that has a value of 3.24. The average now is 4.04. So we're getting very close to the exact amount indeed. Remember, it's 4 is that. So what we've now seen is, as we decrease those widths, that estimate is going to become more and more accurate. Let's look at a rectangle closer, and this time I've just got a random function here, y equals function x, and just one of those, well, rectangles. I mean, the blue amount there is the exact area under the curve, which I'm going to estimate with our rectangle. I'm going to define a new function, and that function is the area function. And if I substitute the value into the area function, it'll give me the answer for what the area is under the curve. So that's the idea. And so I've defined it to be area, and when I substitute C in, I'll get the area from 0 to C. And if I substitute in X, I'll get the area from 0 to X. So the exact area would be the difference between those two. And we want to make that width as small as possible. Okay, so area X minus area C, that is the area that we want. We can estimate it with a rectangle. So there's a rectangle. Its width would be whatever X minus C is, and the height would be whatever we get when we substitute in X into the function, the equation of the curve. Then the area of our rectangle would be X minus C times function X, and we're saying that's going to be approximately equal to area X minus area C. So it's going to be our approximation. Well, if I play around with that and make function X the subject, now why do that? Because that's the known piece of information. We know the equation of the curve. So I know function X. And we're saying function X is approximately this expression. This area function that I've created, which I don't know what it is yet, but area function X minus the area function C divided by this X minus C. Well, instead of writing it as X minus C, I'll just make it one pronumeral. I'm going to call it H. I know it's weird to call it H when I'm talking about the width of a rectangle. You'd think I'd call it W. There is method in my madness, which we will see in a second. So H is going to represent the width of the rectangle. But that means on top, instead of writing X, I could say, well, that's going to be C plus whatever H is. I've got a fraction which looks very similar to something we've seen before. But I'll take it a step further, because what we said was, as the width of the rectangle decreases, the estimate becomes more accurate. So we would like H to be as small as possible. We've looked at another idea called limits. So if I investigate the limit as that approaches 0, I'll end up getting the exact answer. So now I can say this: the equation of the curve, which I know, function X, is actually going to be equal to the limit as H approaches 0 of this area function, which I don't know and would like to know, C plus H minus area C over H. One more step. Because remember, if H is approaching 0, then X and C are pretty much the same value. So I'm going to replace the letter C with the letter X. Now have a look at what we've got. I've got a capital A there. We're used to seeing it with a different letter. But that is our first principles formula. That is the derivative of this area function that I don't know what the area function is. But what I now know is the equation of the curve will be the derivative of this area function that we want to find. Wouldn't it be wonderful if I had a way of going backwards? And that's what we looked at yesterday, the primitive function. So the equation of the curve is actually the derivative of the area function. So we now can work out the area function by finding the primitive function of our curve. It will be the area function. But what we're now saying is, if I want to find the area under this curve, y equals function x, and I know the equation of the curve, I want to find it between two values, a and b. Okay, in my setup there I said from 0, but it could have been from any value I like. So if I want to go from a to b, this is the notation we use. We'll say the area will be, now this symbol here, it's the long S. I don't know if you've ever seen old writing and manuscripts, but when they wrote S, they used to write it as a long S. And that's what that symbol is. Because of course this notation started many, many years ago when they wrote S's as long S's, and the reason it's S is because it stands for sum, because we're summing up a lot of these areas. So that's where the symbol comes from. What we tend to do is we put the limits on either end of the S. So I'm going from A to B, and then we say, well, the curve is function x. That's what I'm trying to find the area function from. That's the primitive I'm going to find. And we say with respect to what pronumeral? Well, with respect to the x pronumeral we're doing it to. That answer will be, I've called it capital F, but it's basically the primitive function. When I substitute in the b value, I substitute in the a value, subtract them, I will get that exact area. So function x is that primitive function we talked about yesterday. This is the process known as integration. This is how we integrate a function. Now let's go back to the question we had before and show you how I got the exact answer of 4. The area under the curve y equals x cubed we were doing, and we were going from 0 to 2. So now I would just set it up like this. I would say, well, that area is the integral, the long S, the integral, I'm going from 0 to 2, and the curve I'm trying to find the area underneath of is x cubed. And I'm going to integrate this with respect to x. In other words, find the primitive function. And yesterday we saw to find the primitive function of a polynomial, we just add 1 to the power over the power. So I've got a quarter x to the power of 4, and those values are 0 and 2. I just substitute into this new function. That a quarter x to the 4, that's my area function. I'll substitute in 2, I'll substitute in 0, and I get the answer 4. And there's the exact value. We are talking about an area, so I should put some units on it. Units squared, of course, would be the answer. Well, that opens up a whole other branch of mathematics for all sorts of other problems that we can still use this same idea. This second example there, I have not said it's an area question. I've just simply say, well, what would be the value of this? Which I can find. Add 1 to the power over the power on each individual bit. Then I'll substitute in 3 minus substitute in 2, and I come up with a number. And you'll notice this time I did not put units squared, because it's not necessarily an area question now. It's simply saying, well, hey, what's the value of this expression? So I don't need to put units on this. That would just be 22 on 3. I said this was for polynomials, but actually any power at all, just like we saw with differentiation, the rules worked when the powers were also fractions and the powers were also negative. Well, going back the other way, the same is true. But I had to find this particular integral, x to the minus 3, add 1 to the power over the power. But a word of warning here, be very, very careful. When you're adding 1 to a negative number, it's so easy to go the wrong way and say, oh, that's negative 4, because you're so used to saying 4 is 1 more than 3. So be careful when it's negative. Add 1, it's negative 2, over that new power of negative 2. Substitute in 5, substitute in 4, and you'll notice I've just automatically converted it out of index form. I just find that easier to substitute into. I can get a feel for 1 over 5 squared. 5 to the power of negative 2, I don't really have a feel for what that is as far as the sizes and what have you. When it's out of index form, I just have a better feel for the number. So it's 1 over 5 squared minus 1 over 4 squared, and all that becomes 9 over 800. Here's an interesting little question. d dx of the integral going from c to x of some function, what would it be equal to? So we're differentiating and then integrating. Well, let's work out what it is we're actually differentiating. We would integrate function t and get the primitive function, which I'll just call capital F. I will get some primitive function, and I'm going from c to x, and I would substitute in function x minus function c, and now this is what I'm differentiating. Well, if I differentiate the primitive function, then I'll get back to my integral. I'm going backwards. It's like inverses cancelling each other out. However, when I substitute this constant number into the primitive function, I know I'm going to get a constant number. And okay, I don't know what that constant number is. But what I do know is when I differentiate a constant number, I get 0. So it actually does not matter what c is. That will always be 0. Meaning, essentially, they cancel each other out. If you differentiate the integral, you just get the function that you were integrating in the first place. So we get function x. They are inverses. They cancel each other out. Okay, 5a and 5b, welcome to the world of integration, which is just going to open up so much more maths we can do.